Okay, so now we will continue chapter 12. And now, if you remember from last time, what we say that a no-gamma austenite will transform according to the Utic iron carbide. Chapter 11 provided to us this beautiful diagram over here, which can tell us that if you cool below this Utic temperature, gamma austenite is going to transform to pearlite that's composed of gamma plus iron carbide. Okay, great. Now, last class we say that what's gonna happen. We try to answer the question of what's gonna happen if you cool down to different temperature. Does it matter or not? Does the pearlite gonna look different or not? Also, how much time it takes in order to have the gamma austenite transform into the final product? Which gonna determine the final microstructure. We say that is the how much energy we're providing. So if you cool down to lower temperature, you're gonna provide much less energy to the carbon atom. So the carbon atom is gonna have shorter diffusion length. And as the result of that, you're gonna have different pearlite compared if you have higher temperature. And also the main difference is if you go to lower temperature, larger delta T, right? The nucleation of the new phase is going to start much earlier compared with the nucleation if you are at higher temperature. So the new phase first is going to nucleate and then it start to grow to consume the mother material. For example, pearlite gonna grow to consume gamma austenite. And also we say that if you cool down to higher temperature, because carbon has more energy, it's gonna diffuse longer distance, and that's gonna result in thicker layers, what we call it coarse pearlite. And if you cool down to much lower temperature, or relatively lower temperature compared with the coarse pearlite, what you end up having a thinner layer because you're providing less amount of energy to the carbon. As the result of that, you end up having what's called fine pearlite. In terms of their mechanical properties, the coarse pearlite is relatively soft, and the fine pearlite is relatively hard. So for you as an engineer, you have two options, right? You can either have coarse pearlite or fine pearlite according to which mechanical properties that you're looking for, because microstructure gonna play a major role in determining the mechanical properties of the material. Then we said if we take for each temperature we can draw or plot this S shape. For each temperature we can plot the S shape, and then we can transform this S shape into 3 points: start, middle, end. Right? So start, middle, end, start of the transformation, middle of the transformation, end of transformation. That will end up helping us in drawing 3 curves that is telling us how much time we need at each temperature in order to transform the austenite into the final product. Right? And we say that we call this diagram TTT diagram. Okay, wonderful. If we take an example here, if you cool down from above the Utic temperature, and if you cool down, let's say to 625, right? So if you wait here, actually nothing is happening until you hit the green curve. Once you hit the green curve, now the transformation of the gamma austenite will start, right? Because we say that the nucleation gonna take time, right? And then if you hit the dash line, 50% of the mother material or raw material عندك الجاما austenite transform to pearlite. If you hit the red curve, then all the gamma austenite transform to pearlite. Okay, and we say it depends. If you are cooling to higher temperature, you're gonna get coarse pearlite. Lower temperature, you're gonna get fine pearlite. Now remember one important information. This diagram, for this diagram, we are fixing the composition. So this diagram it's only for 0.76 weight percent of carbon. 0.76 weight to fix the composition, and now we are looking at the temperature versus time, right? Because in chapter 11, we are looking at the temperature versus the composition, right? So we say, let's pick one composition and let's look at the TT diagram of it. But in case if you are in lower or higher composition, then we have to change the way this diagram gonna look like. Okay, for example, so this is the eutectoid composition. This is how the diagram gonna look like. If you have hyper-eutectoid, let's say we have 1.13, that means you have composition that is higher than the eutectoid. Now we have gonna have some modification to this diagram where you're gonna get additional curve over here, right? In that additional curve, if you hit this orange curve, معناته إن عندك الأوستنايت جزء منها حيتحول لسمنتايت. الأوستنايت جزء منها حيتحول لسمنتايت. And then once you hit the green curve, now you start to transform the remaining austenite into perlite. And once you hit the perlite, the red curve, then all the remained austenite transform to perlite. Okay, so let's say, let me give you an example. Okay, if you cool down to this temperature and then you look at what's going to happen at this temperature, part of this austenite will be transformed to cementite, and the remaining austenite will start to transform perlite. And then by hitting the red curve, all the austenite, the remaining austenite, transform to perlite. Okay, the question now, what's going to happen if we cool down below 540 Celsius? Okay? Now remember, طيب ايش قلنا? We said that if you cool down to higher temperature, you get coarse perlite, thicker layer, carbon has more energy, it can diffuse longer distance. If you cool down to lower temperature, what's going to happen? Carbon going to have less energy, shorter diffusion length, and the result of that is you're going to have thinner layer. Now, if you provide much less energy, what's going to happen? Well, actually the iron carbide will not exist as layer. Well, it's going to exist as elongated as needless particles, elongated particles. You can see here cementite. So you're going to have a matrix of alpha. Okay, let me draw it here. طيب, just want to point very important information. هذا اللي هنا طيب اللي داخل هنا هذا هو الباينايت. It's called binite. Okay, it's called binite. يتكون من ايش؟ يتكون من الماتريكس، the matrix alpha ferrite، الخلفيه حقته alpha ferrite، and those elongated particles ولا اللي هي needless particle تسمى ايش؟ اللي هي الايرون كاربايد. معناته the carbon does not have enough energy actually to form what? To form the thinner layer. Okay, great. So معناته هنا we form another microstructure. It's called Binite Microstructure, and it has needless ore plates. So you have الفرايت exists as a matrix, وعندك iron carbide exists as elongated particles, as you can see here. So this is the iron carbide as elongated particles in the matrix. زي يعني الرز باللبن، ها you know اللي هو الرايس بودينج. طيب، so البودينج عندك الاساس القوام اللي هو الالفا، والايرون كاربايد will be the rice, the elongated particles. Okay, so the way it's going to look like a needless or a plate, and that product is called what? It's called binite. It's called binite. So now we know something called perlite, and today we learn something about something called binite. طيب. Now, very important information is once the austenite transformed to perlite or binite, transformation to another microstructure is not possible. يعني ايش؟ What does it mean? إنه الأوستنايت is the raw material that is not stable. So austenite is the phase that is willing to transform. أما البيرلايت إذا تحول لشيء للبيرلايت, البيرلايت can stay as it is. Even if you cool down to room temperature, nothing can happen. It will stay as it is. الباينايت, nothing can happen to it. Even if you cool down to room temperature, تمام? Because they are stable. The only way to change their structure, يعني to change the binite to something else or change the perlite to something else, you have to reheat again. واضح؟ واضح؟ إذا معناته upon cooling, if a fraction of the austenite transform to perlite, it will stay perlite forever. If fraction of austenite تحول إلى binite, it will stay binite forever unless you apply a heat. Okay, and this is how the TT diagram gonna look like. Ya salam. This is how the TT diagram gonna look like. So this is the rest of the diagram. So before only we look at up to here, right? And now we're gonna look what's gonna happen if you cool down below the 540, below 540, right? So now we're gonna start to have what's called binite. Wonderful. Now I would like to bring to your attention that in perlite, we said that we might have pre-eutectoid phases, right? Similar to here. طيب قلنا هنا إنه ممكن you can get pro-eutectoid phases. like هنا عندك الأوستنايت سمنتايت, قلنا إنه ممكن الفاينل برودكت عندك هنا جزء من الأوستنايت تحول إلى سمنتايت and part of it will transform, the remaining will transform to perlite. فالفاينل برودكت هنا عندنا عبارة عن إيش؟ عبارة عن perlite plus pro-eutectoid cementite. مرة ثانية. If you cool down, let's say to 670 مثلا هنا, طيب, what's gonna happen? Part of the austenite will transform to pro-eutectoid cementite, and the remaining will transform to perlite. معناته the final product over here will have perlite plus pro-eutectoid cementite. Well, for binite, اللي يصير ايش؟ For binite, we cannot see a pro-eutectoid. So pro-eutectoid cannot coexist with the binite. Okay, great. معناته, and from this slide we can answer the following question: what will happen if you cool the material to temperature between 215 and 540 Celsius? Well, what's going to happen is you're going to end up having a new microstructure. This microstructure is called binite. It looks like it has a needleless or plates shape, where the alpha matrix will be the matrix, and iron carbide will exist as elongated particles. And also, in terms of the TT diagram, we have additional. We're going to continue the curve as you see here, where if you hit the green curve, you start the transformation from austenite to binite, and then if you have the dashed line, 50%, and then 100% will transform to binite. طيب. الآن نطرح نفسه. إذن if you cool down to higher temperature, you're going to form coarse perlite. Carbon has more energy. It can diffuse longer. It can form thicker layer. If you cool down to a little bit lower temperature, what's going to happen? Carbon has much less energy, وبالتالي carbon has less energy, وبالتالي has shorter diffusion length, وبالتالي you're going to form thinner layer. If you cool down to much lower temperature, carbon going to have much lower temperature, so the iron carbide will not exist as layer. Well, it's going to exist as elongated particles. The question is, what's going to happen if you take it from here all the way to room temperature, right? That معناته you are not actually providing energy to the carbon. The carbon cannot diffuse and they cannot move. It's like you are freezing the carbon in their position. طيب. So what's going to happen, you're going to form very interesting microstructure. And that microstructure is called, Martensite. Okay, it's called Martensite. So that microstructure is called Martensite. Okay, so a product called Martensite will form as a needle-like or plate-like if you quench or rapidly cool the material to lower temperature. Remember, perlite has two phases. It has alpha wa iron carbide. Binite has two phases, alpha and iron carbide. But the difference between perlite and binite is the way the microstructure is going to look like. Now, Martensite has different microstructure. 1, 2, it has only a single phase. It's called Martensite. So it does not compose of alpha and iron carbide. Okay? And if you look at the micrograph over here, those black plates over here, plate-like or needle-like, you see over here, this is the Martensite. The white region actually is austenite that did not have time to transform into Martensite. This is the remained Martensite, remained austenite. بالتالي the black needles over here is the Martensite. طيب بالتالي هنا عندنا المارتنسايت is diffusionless transformation. Carbon diffusionless يعني ما صار له diffusion. The carbon does not have the time to diffuse. بالتالي is diffusionless transformation of austenite, where gamma, it has FCC structure, will transform to martensite that has body center tetragonal, BCT, body center tetragonal. طيب the difference between BCC and BCT, BCC اللي هو body centered cubic. Body-centered cubic. In body-centered cubic, if you remember, we have atoms in the corners and plus atom in the center. It's called BCC. And we have a cubic unit cell. Now BCT, you have tetragonal unit cell, where the A equal B but does not equal C. So it's a little bit longer. This is called tetragonal. It's body-centered because you have atoms at the corner plus you have atoms in the center. ممتاز. إذن إيش اللي صار هنا؟ في هذا البي سي تي هذا iron atoms. طيب. Now at the edges the carbon will be locked. طيب. It will freeze at this position. It cannot move anywhere else. طيب. بالتالي the carbon will diffuse in these positions as you can see over here. طيب. بالتالي the carbon cannot diffuse to form new phases. It's going to only form one phase اللي يسمى ايش؟ What's called the Martensite. طيب. So all carbon atoms remained at interstitial impurities, so they form supersaturated solid. Thus they are capable of transform to other structure upon heating. طيب. الآن هذا المارتنسايت قلنا البيرلايت والباينايت عفوا المارتنسايت is non-equilibrium single phase structure. Non-equilibrium معناته انه if you leave it for longer time or maybe you heat it, طيب, what's going to happen? It might transform to other microstructure that's more stable. طيب. Okay, great. So the transformation is instantaneously occurred with the martensite nucleate and grow very rapidly. So you have BCT and the few slip planes. بالتالي in terms of mechanical properties, we're expecting this martensite to be very hard and very brittle. So the main message of this slide is telling us if you rapidly cool the material from austenite to room temperature, the result microstructure, the final microstructure will be martensite. Martensite is composed of a single phase Mahi is not composed of alpha and iron carbide. It's composed of a single phase, which is BCT, where the iron has a BCC. It has located at the corners plus the center, and the carbon locked in the interstitial position between the iron. طيب, once you have martensite, very hard, very brittle, can you enhance the mechanical properties? The answer, yes, you can enhance the mechanical properties. But enhancing the mechanical properties is going to require from us to change the microstructure of the martensite, right? The way that we can change the microstructure of martensite is by providing heat, right? So if we take this martensite and we provide more heat, we can change to something else. It's called timbered martensite that I'm going to touch upon in few minutes, inshallah. Okay, let's now look at how the TT diagram going to look like now with perlite, binite, martensite. Okay, ready? Okay, this is how the TT diagram going to look like. TTT diagram. The first portion going to have the perlite. Second portion going to have the binite, and then if you cool down below 250, going to have martensite. يا سلام. لاحظ هنا, pay attention to very important information. إنه if you cool, martensite does not depend on time. It's only depend to which temperature you are cooling. For example, once you have this temperature, now 0% transformation. If you have this temperature, 50% transform to martensite. If you cool down below this temperature, let's say to room temperature, what end up having? You're gonna end up having full transformation of you're gonna have 90% of the martensite of austenite transformed to martensite. Martensite is not similar to the perlite, the binite in terms of their dependence. Its dependence on the time. So it only depends on the temperature. However, perlite, binite depends on the temperature and also depends on time in order to see the transformation. Martensite only depends on the temperature. This is why we call martensite transformation we call this a thermal transformation, because it's time independent of time. It's independent of time. That's why we call the gamma austenite to martensite transformation, we call it a thermal transformation. Okay, again, if we would like to enhance the mechanical properties of martensite becomes hard, brittle, we're going to always, there is a way to enhance the ductility by providing heat. Now, if you provide heat to the tempered martensite, this is how the microstructure is going to look like. Actually, if you provide heat, now the carbon can get out from the BCT structure. It's going to get out and will start to form sphere-like particles. Sphere-like particles with very, very small spheres. How the small spheres is the iron carbide particles, right? And the matrix gonna be the alpha matrix. Okay, so that means if you take this one, martensite does not have alpha, does not have iron carbide, and you heat it up, the result will be you're gonna end up having small spheres, وهذه الspheres اللي هي iron carbide in the matrix of alpha. Okay, and now this is called timbered martensite. So what will happen if you reheat the martensite material below the ejector temperature between 250 and 650? يعني أخذت المارتنسايت الآن بعد ما تحول المارتنسايت and then you reheat it again to higher temperature, well, diffusion will be possible, because in martensite it's diffusion-less. Carbon cannot diffuse. Now you're providing energy with the carbon to diffuse. Wonderful. So the diffusion process where the internal stresses might relieve even at 200 Celsius. ايش اللي حيصير؟ What's gonna happen? Martensite will transform to timbered martensite, which composed now of two phases, alpha plus iron carbide. طيب. The microstructure gonna look like where you have small and uniformly dispersed cementite particles embedded within continuous ferrite matrix. طيب if you هنا ايش مكتوب؟ مكتوب انه if you reheat if you reheat the martensite. So if you reheat the martensite to temperature between 250 and 650, you start to transform martensite to tempered martensite, where the iron carbide is going to have small spheres. طيب okay. طب ايش يصير if you keep it at longer time, يعني reheat it and you keep it for longer time, هذا small particles are going to become larger. ليش? Why? Because we learned earlier that the larger the particle, the less is the interfacial area between the carbon and the matrix. تفتكروا في الجرين boundary قلنا grain boundaries prefer to have larger grain boundary compared with smaller one, because if you have smaller grains you have higher energy. Similarly here, if you have higher interfacial area between the iron carbide and the surrounding matrix, ايش اللي حيصير؟ you have higher energy. So if you provide some heat to the material, those iron carbide become now larger. Why? Because it wants to reduce the interfacial area between the iron carbide and the alpha ferrite. طيب. This is what's going to happen to martensite. But what's going to happen to perlite to binite? Because we said perlite binite are stable. If you cool down even to room temperature, they say as it is. Right? What's going to happen if you take perlite binite and you heat it above, heat a high temperature just below the eutectoid temperature? Well, what's going to happen? So what will happen if you reheat the binite or perlite material just below the eutectoid temperature for a long time, يعني from 18 to 24 hours? Well, what's going to happen? Instead of having alternating layers or elongated particles of iron carbide, what's going to happen? They will try to come in a sphere shape. Right? They can come in a sphere shape. In a sphere shape, so iron carbide is going to have sphere-like particles. Now imagine if you have this, if you have alternating layers of alpha and iron carbide, right? If you have alternating of alpha and iron carbide, now you have more interfacial area between these two, right? So you have more interfacial area between the two phases. If you provide heat to the material will say, can I minimize the energy? And the answer is ready. Yes, you can minimize the energy. How I can do that? Reduce the interfacial area between the two phases. How we can do that? Well, start to let the iron carbide form like a sphere shape instead of having a layer. This is why when you have a water, right, similar to the water drop, when you have a water drop, the water is going to assume as kind of a sphere-like shape, because that's going to minimize the energy of the water droplet. So most of the water will be inside. You have less interfacial area between the water liquid and the air outside. Okay, wonderful. So what's going to happen if we reheat the binite and perlite below the eutectoid temperature for longer time? Well, you're going to form spheroidite. Spheroidite. Now we learn about perlite, coarse perlite, fine perlite. We learned about binite. We learned about martensite and tempered martensite. And now the final product is called spheroidite. Spheroidite because it's sphere-like. But what is the difference between this one with tempered martensite? All of them, they look like sphere. Yes, they look like sphere. But martensite, in martensite, the cementite particles, they have sphere-like shape, but they are much smaller compared with the spheroidite. يعني الspheroidite هنا عندها larger particles. حلو? Larger sphere particles. Okay. What we learn in chapter 11 is that we learned something very important. if you start to add other elements other than carbon, you can actually play with the eutectoid temperature, and also you can play with the eutectoid composition. Similarly, if you add other elements, you can, other than carbon, if you add other elements other than carbon to the iron, you can change how the TTT diagram going to look like. Well, let's look how the TT diagram going to look like. Okay, wonderful. So here you get, this is how the modified TT diagram going to look like if we add other elements such as chromium, nickel, molybdenum, silicon, and other elements. Okay, so the main difference is now you have two noses instead of one, right? Because initially you have only one nose, Imam, and now here you have two noses. One is for perlite, one is for binite. This is the main difference number one. Difference number two, you notice that we have shifting. We have some shifting of the transformation for longer period. Compare with the an alloy that does not have this additional elements. Now that means when you add elements other than carbon, you are delaying the transformation of gamma austenite to alpha plus iron carbide. Whether it's perlite or binite, so you're delaying this reaction. Okay. So let me stop here, and in next lecture, inshallah ta'ala, what we'll do, we will tap into different questions, set of questions. A very important question is, what's going to happen if we play with the cooling rate? So far, we did not call about the cooling rate. We talked about what's going to happen if you cool to different temperature, what's going to happen over time, what's going to happen if you add other elements other than carbon. In next lecture, we're going to talk about what's going to happen if you control the cooling rate of the material. And we're going to have different diagrams called CCT, which means continuous cooling transformation, which is going to look like similar to the TTT diagram with slight modification. But we're going to do is we're going to look at different cooling rate and see how different cooling rate might end up having different microstructure. Different microstructure. So I'm going to stop over here and inshallah continue in next class.